Welcome to lecture 10. In this lecture, we study equality of mixed partial derivatives. Okay, so topics of this lecture are following. This is page number 1. Topics are following. First, we give some definitions. Then examples. So then main question, and finally the main theorem. So let us start with definition of partial derivatives, or uh, more precisely mixed partial derivatives. Okay, so definitions. Let f be a function from Rn to Rm. Okay, so f equal to f1 and so on fm. So these are the component functions. This is a function from Rn to Rm. Okay, so let this be a function. Then the ith partial derivative of f denoted by dif. So this is again a function from Rn to Rm, where I lies between 1 and so number of variables, that is n. Okay, and this is first order partial derivative. Then for every I lies between 1 and n, integer lies between 1 and n. This is the first order partial derivative is defined by dif at the point x. This is equal to dif1 at x, and so on difm at x, where dif sub k at x, this is equal to limit f sub k at x plus t e I minus f sub k at x over t limit t tends to 0, and k lies between 1 and number of component functions, that is m. Okay, so this is the ith partial derivative of kth component function fk. Okay, so this is the first order partial derivative, of f. So now we defined. So this is again function from Rn to Rm. So provided these limits exist. The limits exist. This is page 2. And similarly d j comma I f, this is equal to d jth partial derivative of the first order ith partial derivative of f, and this is again function from R n to R m is similarly defined. For all 1 lesser equal to I comma j lesser equal to n. Okay, so and these are called second order mixed partial derivatives. Second order mixed partial derivatives. Okay, so now, so these are the definition. So next topic is examples. So consider function from R2 to R, that is n equal to 2, m equal to 1, defined by f of x comma y, this is equal to x times y times x square minus y square over x square plus y square. So x comma y should not be 0 comma 0, and for x comma y equal to 0, this is equal to 0, x comma y, this is equal to 0 comma 0. Okay, so let us compute partial derivatives of the function f at 0 comma 0. So d1 f at 0 comma 0, this is equal to limit t tends to 0. So we are following the definition. F 0 plus t e1, so this is the first variable. So 0 plus t e1 means t e1 minus f 0 comma 0, okay, over t, and this is equal to limit t tends to 0. So f of t comma 0, so te1 means t comma 0 minus f 0 comma 0, that is equal to 0, so over t, and this is equal to this is equal to limit t tends to 0. So y here, y component is equal to 0, so it is numerator is 0 over t, so limit is 0. Okay, so the first order partial derivative of f with respect to the first variable at the point 0 comma 0 is equal to 0. This is page 3. Now for x comma y not equal to 0, we have d1f at x comma y. This is equal to so x square plus y square and derivative, so this is denominator times derivative of numerator with respect to x, and that is equal to 3 x square times y minus y cube minus numerator times derivative of denominator with respect to x, that is 2x times numerator is x cube y minus x y cube over x square plus y square whole square, and this is equal to y times x power 4 plus 4 times x square y square minus y power 4 over x square plus y square whole square, and this implies d1f 0 comma y, this is equal to put x equal to 0 here, so x equal to 0 here, x equal to 0 here, and so on. So this is equal to minus y. Okay, so check it. Okay, so and this implies d 2 comma 1 f at 0 comma y, this is equal to minus 1, and this implies d2 comma 1 f 0 comma 0, this is equal to minus 1. So on the other hand, we have d2f x comma y when x for x comma y not equal to 0, so we have d2f of x comma y, this is equal to, so I am not going into the detailed computation, this is equal to x times x power 4 minus 4 x square y square minus y power 4, okay, over x square plus y square square, and this implies, and also d 2f at 0 comma 0, so this is equal to 0, d 1 comma 2 f at 0 x comma 0, so put y equal to 0 here, so this is equal to x, okay, and this implies d1 comma 2 f 0 comma 0 equal to 1. So we have d 2 comma 1 of f at 0 comma 0 equal to minus 1, and here we have d1 comma 2 f at 0 comma 0 equal to 1. So this implies d1 comma 2 f at 0 comma 0 is not equal to d2 comma 1 f 0 comma 0. Okay, so now we have the following natural question. This page 4, third part question. Under what condition or conditions or when the two mixed partial derivatives that is d1 comma 2 f and d2 comma 1 f will be equal. More generally, under what condition or when two mixed partial derivatives d, let's say r comma k f and d k comma r f will be equal. So when the function f is from Rn to Rm, okay, and r comma k lies between 1 and n. So this is the general question, and so answer of the question is the main theorem, page 5. So this is section 4, main theorem. Theorem 1. So theorem 1 answers the question just we have asked. So the statement of the theorem is following: if both the partial derivatives, the first order partial derivatives, drf and dkf exist, and so exist where? Exist in an open ball B C comma delta. So this is open ball with center at C and radius delta. So delta is some positive real number, so this is equal to x belongs to Rn such that norm of x minus C less than, strictly less than delta. Okay, so when both the first order partial derivatives drf and dkf exist in an open ball B C comma delta, that is open ball with center at C and radius some delta greater than 0, and furthermore and if, so this is the second condition, if both differentiable at C. So both differentiable, that is the rth partial derivative of f drf and dkf, the kth partial derivative of f, okay, they are differentiable at the point C. Then dr comma kf at C equal to dk comma r f at C. Okay, so we label this equation by 1. Okay, so in the next part we prove this theorem.